Behind the Black Mirror, simulating attacks with Mock C2 servers. In this presentation, I'm going to be presenting an approach we've taken to more realistically simulate malware attacks in order to improve our overall defensive capabilities. First, a little bit of information about me. My name is Scott Knight. I'm a threat researcher on the Threat Analysis Unit team at VMware. I reverse engineer malware, I track threat actors, and I work to share the information back with the security community. In this talk, we'll cover what a Mock C2 server is and why you might want to create one. And then we'll go into the process for actually creating a Mock C2 server. From there, I'll talk about some common C2 protocol characteristics that we often see and get into the details of how we go about simulating attacks using a Mock C2 server. I'll be demoing a tool that we've been working on to make the entire process easier. So what is a Mock C2 server? Well, in programming, a mock object is one that simulates the behavior of a real object in order to facilitate software testing. We take that same concept and apply it to the malware. So a Mock C2 server can be thought of as a server that is simulating the behavior of a real C2 server to accomplish the same goal in order to test and analyze the behavior of the malware. So why would you want to create one of these? Well, during reverse engineering, we spend a lot of time doing static analysis, and that gets us a large portion of information about what the malware might be doing. But dynamic analysis really allows us to go further and determine much more than we otherwise normally would be able to about how the malware actually behaves in real situations. This dynamic analysis can be very challenging if you don't have a C2 up and responding. Some malware, all they do is attempt to connect to its C2, and if there's not a server listening, then they simply stop and do nothing else. So, often we only see a small subset of the capabilities as we're trying to observe malware running. Another reason why you might want to create one is if you're interested in tracking different malware families. The network protocols and the network traffic are often a good way to track some of these families, but it's very hard to reverse engineer a network protocol if you don't have a piece of malware that's actually communicating over the network with something. And finally, it's the improved visibility into how the malware would behave in a real world attack. Again, we can detonate malware in a lab environment and maybe see that it sends a beacon packet. But if the malware was used in a real attack, what are the typical behaviors that we might see? So let's talk about how you would go about creating a Mock C2. The first step is really the most straightforward. You just want to pick a programming language. And there's really, I think, two paths you could go down, either kind of using a scripting language or using a compiled language. There's pros and cons of each. With scripting, you have your typical languages like Python, Ruby, Node.js. And a lot of these languages make it very quick, very easy to get something up and running. They have lots of different third-party packages that you can use. And because it's a scripting language, it's easy to take it to any platform that you want. Conversely, with the scripting languages, it can sometimes be harder to work with the binary data that you might have as part of a network protocol. And you just have to be a little more conscious of how you're interpreting the bytes that are being sent across the wire. Compiled languages, again, there's a lot of different choices. You have newer languages like Go, Swift, and Rust, but also just a normal C program works just as well. Often you'll have improved performance and better concurrency support in some of these compiled languages that you do in some of the scripting languages. But it can be challenging at times for building projects or bringing in third-party dependencies. It can be somewhat error-prone. There's no real wrong answer here. With the goal of essentially simulating a server so that you can analyze the malware, it's important to keep in mind that your ultimate goal is to analyze the malware. So you're not looking to create engineer the best C2 server that you can. You're looking to get something up and running quickly. So whatever language you're most comfortable with, whatever language that you work the best in, is probably going to be the right choice. The next step is really setting up your network in order to allow the malware to talk to your C2 server. So you're going to need at least one machine to be a mock C2 server and another machine where you can run your malware or detonation host. Both machines should be on the same network. In this case, virtual machines and virtual networks make this very easy. You should be able to spin up as many machines as you need, put them on the same network, and get things going. From there, you really have to consider how the malware is identifying its C2 and trying to connect. If it's using DNS, domain names, in its configuration, then it's fairly easy to set up your detonation machine so that you can simply modify a host file and point the domain name to your own IP address, your own mock C2 server, and get the malware talking to where you want it. In the case of hard-coded IP addresses, if you've taken the time to set up 2 virtual machines on a virtual network, then this isn't that much more difficult. Essentially, you want to identify the C2 IP address and set your mock C2 server to have the IP address of the real C2 server. Then by modifying your detonation host to have an IP address on that same subnet, essentially when the malware goes to talk to its C2 server, instead of being routed over the internet, it's simply going to talk to the other machine on your virtual network. The next step is just to listen. Essentially, you want to start a server listening on the port that you've identified through reverse engineering. And again, this should be quick. You want to use the language that's going to let you get to this point as quick as possible. And most any language you pick is going to make it fairly easy to simply start a server listening on some port. And from there, don't even worry about coding anything more complicated than just listening on a port. Use a tool like Wireshark and start to capture traffic. Now that you have a server that's up and listening, Wireshark is a great tool for starting to explore what is the malware sending, when is it sending, what's the format, and just looking and seeing what shows up. From there, it's kind of an iterative process. You'll start your dynamic analysis using Wireshark, and starting to look at the data and see, well, what format are my packets in? Does it look like the data that's being sent across is encrypted? Am I seeing some packets sent over and over again that look like they're the same, and maybe the malware is beaconing out? Does it seem like the malware is expecting a response? From there, you just want to work to add the minimum amount of mocked out responses as you can. Because again, the goal here is speed, and the goal is to analyze the malware, not to build a complete mock C2 server. So, if you see that the malware from static analysis is sending out a packet and then expecting a response back, then add that to your mock C2 server and kind of repeat this process. Send the response, see what comes next across in the network captures, and continue from there. So let's touch on some of the common things you'll find in C2 protocols as you're iterating and sort of stubbing out functionality. The first thing is really kind of the network and the encryption. It's the first hurdle in understanding how the malware communicates, and you really need to determine, well, what transport mechanism is the malware using? So far, I've kind of assumed that it's using TCP, but you could have malware that's using UDP as well. In which case you'd have to kind of start your mock server in a slightly different way. But also things like, is it using standard protocols? Like, is it communicating over TLS? Is it communicating over HTTP? You may start to look at some of the packets and realize that it's using something that looks like TLS, but isn't exactly TLS. These are probably some of the more common mechanisms that we see. When it comes to the encryption, it's fairly common that a C2 protocol is going to have some way to try to obscure the real payloads that's being sent and received. So you may be able to see header information, but you may not see the actual payload that's being sent. If your goal is to create a server that can talk to the malware, though, it's going to be necessary to reverse engineer whatever encryption is being used in order to create a properly working MockC2 server. Again, here, there are some common patterns that show up. And so we're going to look at a handful of them next. The encryption can often be one of the harder steps of mocking out a protocol. So first we have just a simple XOR. I would say that this is very common. It's easy to spot in packet captures. Whether you have a single byte or a short key that's repeating over and over again, it often leads to patterns in the network data that can be easy to spot. In the case of a single byte, if the malware is sending data that has zeros, then you may see the actual key echoed back in the network data, repeated over and over and over again. Usually this is easy to reverse as well because it's not doing anything very complex. On the left over here, you can see a sample where it's got an array of bytes in this data array, and it's just looping through the entire length and XORing each byte with the byte 77. Another common approach that malware authors will take are kind of using a more complex XOR. You might call this, quote, custom encryption, but at the end of the day, it's really just taking each byte and XORing it with part of a key. In these cases, it's usually the key derivation that can be a little more complex and in turn can be a little harder to reverse. It will do a better job of obscuring the network traffic because you're not going to see as many bytes repeating or patterns in the encrypted output. But at the end of the day, it's often just working to determine how is the malware seeding its key and how is it then combining that with the input data. You can see kind of in this example, we've got 3 different seed values. Those 3 values are used to XOR a byte of data, and then those 3 different values kind of change and get mutated. So it's really just one long key stream that's created based on the seed values, and then it's just a simple XOR of all the data. RC4 is another very common one, whether it's used in network protocols or with file encryption. Even though it's an older algorithm, because it's an easy thing to implement without using third-party libraries, it still gets used a lot. It's fairly easy to spot when reversing. You can often look for the RC4 initialization. So you can see, in this example, there's a for loop going from 0 to 255, and it's simply taking each of those values and filling in an entry in an array. So this is the RC4 sbox initialization. AES is another common one. I think a lot of malware authors feel like it's more secure, but it really all depends on how they create a key for the algorithm. It's usually easy to spot when reversing. It tends to use standard APIs, standard libraries. You can see in this example, the malware is calling crypt-derived key, which is a Windows API, and it's passing in a constant for AES 128-bit encryption. In this case, I think because malware authors know that they're using a standard encryption algorithm, and that defenders can also, take the standard algorithm to decrypt traffic, they often work to obscure their key derivation a little more or make it more complex. And that's how they try to provide security to their protocols. One final thing to kind of consider is how the malware sort of initiates its communication channel. So it could have a handshake where it's working to ensure that it's talking to who it thinks it's talking to. And it could also perform some sort of key negotiation as a way to try to have a more secure communication channel. This is usually more complex to reverse and mock, but on the flip side, it can make network detections easier. It has a more distinct fingerprint to the network traffic. In the example here, in red, we have the malware sending requests out to the C2 server, and in blue, we have it listening for a response. And you can kind of see that it's got this process of sending a number, expecting another number, and then writing a third number. And unless this happens, it's not going to communicate with the C2 server. The command structure itself is something that is often not that different across malware families. As you're using a tool like Wireshark and listening for the traffic and starting to inspect the packets, there's a handful of different things that you can look for to start to get an idea, at least, of the structure of the data. So any sort of, quote, small number, whether it's 32-bit or 64-bit, you're going to see zeros show up in it. So, in red here, we see a number E290000, which appears to be a 32-bit number stored in Little Endian format. We kind of continue scanning across, and we see like another chunk of data, 4 zeros in a row, and then another small number, 41, also in Little Endian format. The byte ordering is important. Sometimes you'll see Little Endian, sometimes you'll see Big Endian, since that is used for network byte ordering. Another thing just to kind of look for as you're going through your packet captures are just any sort of ASCII or Unicode characters. We talked about encryption, and that can be the most difficult part, but there's times where you will have things that aren't encrypted, and looking for printable ASCII or Unicode is a good sanity check in terms of determining whether something is encrypted or not. Once you've identified these chunks, then there's some common fields that tend to show up over and over and over again. Assuming the malware provides the ability to run commands from the C2 server, you're often going to find either like command ID or a command opcode that's indicating, okay, well, what type of command is this? As well as you'll have usually a length and then the actual payload itself. So in this example in yellow, we have hex 41. And if we look at the data that comes after it, we have exactly 41 bytes of data. So we can kind of assume that that field in yellow is a length, and then the blue is the actual payload. You can get a pretty good rough idea of the format of these payloads from the static analysis. But there's a ton of value of actually sending some of these commands and running the malware and even debugging it to try to see what it does. It doesn't take a lot once you have a C2 server up and listening to send the basic command, even if you don't understand the format of the payload yet. You can start to play around and kind of test like you were almost a QA department, and sending a command and seeing, well, what happens when I don't send any data? What happens when I send data that's too big? What happens when I send data that looks like this? And it will let you start to understand better, how does the malware handle the data that's coming in over the network? How is it decoding it? How is it interpreting it? There are different types of commands that we usually see malware protocols supporting. Typical ones are a beacon of some sort. So the malware basically starting up and attempting to contact the C2 server and inform it of who it is. From there, supporting some basic form of viewing what processes are running on the machine. Viewing and doing file manipulation is fairly common. And then upload and download of files and command execution. With even just this limited command set, there's a lot that a C2 server can instruct malware to do. There are less common types of commands that we have started to see more often. Things like screenshots or live screen viewing, microphone recording, key logging, those types of things. But ultimately, it definitely requires, I think, more development work on the malware author's side to create these more complex commands. And at the end of the day, if they have command execution, you're going to accomplish a lot of these same tasks just by executing a command, saving the output of a command, and then downloading it back to the remote server. So simulating attacks. What is our approach here? So we have been creating these Moxie2 servers, again, kind of as I described earlier, as quick as possible, get something that's up and working, and test the malware. And you can kind of see in this screenshot here that the goal is to kind of go from the state on the left where we're maybe only seeing beaconing to the state on the right where we can see all the different functionality of the malware. So we've been working to consolidate our Moxie2 servers into a centralized tool with the goals of, we wanted to make it easy for researchers to reverse and implement new protocols. And on the flip side of that, we wanted to make it easy for anyone to simulate an attack, as well as provide a user interface that red teams are already used to. So I'm going to go over a demo of the tool that we just call Moxie2. So I'll start by starting up our tool. It provides an interactive command line interface. I can get help. Essentially, though, we want to start a listener. So if I say listener start, and it has tab completion, and hit tab, we can see the different malware families that are supported by the tool currently. I'm going to start a listener for the Mata family, and I'm going to listen on port 443. So if I come over to my virtual machine now, where I have the malware installed, I'm going to go ahead and start running the malware. And then I'll come back to my terminal, and we can see that an IP has connected. Mata command has been sent, and it has been acknowledged. So from here, I'll run the list command to see who's connected. There's an agent ID. I can use the interact command to interact with the connected piece of malware. From here, I'll type help again, and we can see the list of commands that are available once I'm interacting with an agent. So I'll start just to get some information about the machine I'm on. So who am I, kind of where am I on the machine? And we can see that it returned, okay, you're the fake user, you're on the fake user's desktop. So maybe I want to see what's actually on the desktop. I can see that there's a couple files. In this case, credentials looks like something that might be interesting. So I'll use the download command to download this file to my local machine. And we can see that the first time I'd already downloaded it, but the second time, then it saved it successfully. From here, maybe I want to upload a tool to do some recon on the machine. So I'll upload a tool called SwiftBelt, and then I'll make the tool executable. And then finally, I'll actually run the tool to get the information about the machine that I'm running on. And this is all just output from the tool being run remotely on the machine. So we can see that I'm getting back information about the operating system. It's Mac OS. 10.15.5. I see the user that I am, the home directory, computer name, IP address information, environment variables. It's even searching for credentials. One of the other nice things about the Moxie2 tool is it's got a debugging menu, so I can turn on debugging and execute another command. And this time I'm going to end up seeing essentially the network traffic that's going back and forth. So as you're kind of maybe adding support for a new network protocol, you can kind of work to see what data is being sent back and forth, what commands coming across, what's that command ID, what's the size, what is the actual data coming back, the payload format that's showing up. So a couple just additional thoughts before I finish up. First, I hope that you take away from this talk the fact that mocking C2 servers can have a huge benefit. Providing the ability to put a piece of malware kind of through its paces and having it kind of do more than just send a beacon packet out can really provide a ton of additional visibility and really allow us as defenders to better understand how we can protect our users against these type of attacks. The other takeaway that I hope you get is that it can be easier than you might think to get a Moxie2 server working. Again, with the goal of just starting simple, adding functionality as you need it, you can usually get something up and running pretty quickly. Finally, the demo I just gave of the Moxie2 tool, we're going to be releasing the tool as open source, and I'd love it if folks would join and help contribute more family protocols to make it even easier to kind of simulate these attacks in the future. Thank you.